let's use our knowledge of quotient groups to learn about modular arithmetic. So quotient. So what we're going to do is we're going to consider. So normally we have group G and a normal subgroup N, and then from that we form the quotient group G mod N. So right now we're going to choose G to be equal to the group of integers, and it's integers with addition. So the group of integers where the group law is addition, and n is going to be equal to nz, where we'll let n be some integer, say 3 if you want, and this is a subgroup of the integers. We proved that, and in fact all of the subgroups of the integers are of the form nz for some n. And as it turns out, since z is an abelian group, nz will be a normal subgroup. So this will work, and then we can form the construction z mod nz. So let's think about what the elements of z mod nz look like. It's a set of left cosets of nz in z. And the way we can write that down, so normally we write down cosets like, if A was an element of G, we would write A times N for the coset. But in this case, I'm going to write A plus NZ because my group operation here is addition and not multiplication. So this is just notation. The plus part, or really because the group is using addition as the notation for the group operation. So I'm using addition for the notation for my coset notation. So A plus NZ, and that'll be for A in Z. And right, A plus NZ, this is the set. So each one of these is, it's going to be A plus N, A plus 2N, dot, dot, dot. But you're also going to have A minus N, A minus 2N, dot, dot, dot. I guess I could have written that in order. I could have written all of this stuff over here, and put this over here. Swap these two. It's another in order, but I guess since it's a set, I didn't have to. But that's fine. So this would be the coset. And these are the elements of the group. And the quotient group tells us, the theorem about the quotient group tells us that, A plus NZ plus B plus NZ equals A plus B plus NZ. And of course, we can also see that N plus NZ, or more generally Kn plus NZ, will just be NZ, because Kn is in the subgroup NZ. And so this will, so noticing this will let us have a more concrete description of Z mod NZ, and we can do that in the following way, which is, so right, we said Z mod NZ is a set of A plus NZ for A in Z, but what we can do is A plus NZ will equal B plus NZ if and only if A equals B plus, K times N for some K. So the procedure, so we can take, so given an arbitrary coset, given some A plus NZ, we can take A and we can shift it by N or by any multiple of N, and we'll still have the same coset. So what we can do is we can say we want a procedure that will give us, given a coset, it'll tell us which coset that actually is. So the procedure is given A plus NZ, we can subtract and or add multiples of N, I guess, not copies, of N until A plus Kn is in the set and so let's just choose the set 0, 1, 2, ... n minus 1. So we've chosen this set which has size n, right? We're starting from 0, we're 0 indexing. So this set which has size n, and whatever we have, we can write it as, I guess I should say, k multiples of n, or something like this. But this coset right here is going to be in one of the following, right? So we'll have 0 plus nz, 1 plus nz, 2 plus nz, all the way up to n minus 1 plus nz. And so these form a unique set of what are called representatives of the coset, and so we can regard these as the elements of the group Z mod NZ. So we could say that Z mod NZ equals the coset 0 plus NZ 1 plus NZ ... n minus 1 plus NZ. And what people do in practice is, rather than writing plus NZ out, we'll write, a bar, 0 bar, 1 bar, ... n minus 1 bar. And that bar sort of denotes that this is a coset. And this is what's called modular arithmetic. And the thing about modular arithmetic is we see that modular arithmetic is reflected in normal arithmetic, and right, and so we could also say this is 0 mod n or something, 0 bar. This is another notation right here, and so so this what we can see is that the reason that when we add the equivalence classes, when we add the cosets, the addition is respected. That's reflected in the fact that by the quotient construction theorem, there's a morphism from Z to Z mod NZ. So that means if we want to add two classes in here, we can, pull back to here, add them, and then push forward on the map, and we'll get the same thing. So that's how we add equivalence classes, is sort of by pulling back to where we know how to add in the integers, and then pushing forward on this map. So that's modular arithmetic.